Hello guys and welcome back to my YouTube channel. Today we are going to be discussing ACLs and MPLS. Let's go ahead and dive in. So MPLS or multiple protocol label switching. Instead of making routing decisions based on routes, destination, source IP addresses, things like that, it actually uses labels, and its main focus is actually speed and instead of doing complex lookups to the routing table. It just once it touches a certain router or provider edge router, it's going to get attached to the label, and then it'll go based on labeling and based on the labels instead of the IP addresses. Its main use is really just speed. So technology using labels to direct data packets efficiently, speed faster than IP routing, avoiding complex lookups. It uses labels. MPLS assigns labels to packets, enabling routers to forward them without complex IP lookups, ensures optimal path for data, improving network performance and reliability. And this is what it would look like, right? So let's say this is a customer edge router, and this would be a provider edge router. It will be, once it hits this interface right here, it's going to get slapped with the label. And here, super speed, think of speed just like a race car, right? Vroom, it's going to glide through this. Once it gets here, it's going to remove the label, and then it's just going to get forwarded here using IP addresses, right? Tunneling. So you can think of tunneling like a burrito, right? It's going to protect everything inside of it, and unless you ordered the burrito or made it, you're not gonna know what's exactly inside of it unless you're one of those two people, whether that be the sender, the receiver. Those are the only people that are gonna know what tunneling or what's inside of it, right? Because tunneling encrypts it, right? It's wrapped inside an additional header, forming a tunnel, and it carries through the network. Types of supports traffic, non-IP routables, IPX, MPLS, private data over public networks like the internet. Combined with encryption, again, like the burrito, you're not going to know what's inside of it, right? Prevents from eavesdropping, as in VPN tunnels. And this would be it, right? So this is just like a visual representation of the tunnel. Like it's still going to go through here, but it's just going to be through here, encapsulated, right? Remember the tortilla is going to encapsulate whatever is inside of it. The tunnel, the tortilla, encapsulates it, preventing people who aren't the person who ordered it or who received the order. They're not going to know what's inside of it, right? You're just going to know it's a burrito or it's a tunnel being sent over the network, right? Or data being sent over the network. That's all they're going to know. And then there's type-seq tunnels, the GRE, generic routing encapsulation. This one doesn't provide any encryption at all. So no security, no none of that. It just supports broadcast and multicast traffic, right? IPsec can be combined with GRE to have IPsec over GRE, if I'm not mistaken. This provides the ability to support multicast and broadcast as well as encryption. So that security that GRE alone does not provide, right? IPsec provides encryption, often used in site to site, like let's say connecting an office in Chicago to an office in Daytona, right? SSL/TLS, this is typically used for client VPNs. So you're working remotely, you connect to Global Protect. Once connected, you're going to be able to access internal company resources as if you're physically on campus, right? It mimics as if you're on site, right? Layer 2 tunneling protocol, often combined with IPsec for secure tunneling, right? GRE, again, encapsulates a layer 3 packet, but does not provide encryption and supports non-IP protocols or multicast traffic, right? Can be tunneled over IP networks, does not provide encryption, and see it can be paired with IPsec for routing flexibility and the encryption that IPsec gives as well. And then this is the example. I already have it preloaded, so let's go ahead and do that. There's no configurations on it besides the IP addresses configured. So you can see here, and as well as here. So let's actually go and create a tunnel. So we'll do interface tunnel 1, IP add 192.168.10.1. Do no shut. Then we'll do tunnel source, and then it's going to ask for the interface ID. So it's going to do G0, gigabit Ethernet 0/0, and then tunnel destination is going to be the physical IP address that's here, right? Not the end of the tunnel here. So we'll do 60.60.60.2. Since this is a /30, it's going to be the second available IP address here, since this one was configured with the first one. And then that's it for the tunnel. Do exit. Do the same thing over here. And then I'll actually ping from them using the tunnel to show you that it does get encapsulated in the GRE tunnel, right? Interface tunnel, 1, IP add, 60.60.60.2. Wrong one, IP add 192.168.10.2. Shut. And then we'll do tunnel source again. It's going to be the interface. And then tunnel destination is going to be the IP address of this interface, the IP address of this physical interface here, not of the tunnel. Remember that, okay? So it's going to be 60.60.60.1, and that should be enough. And then let's do end. Let's do ping, and then we'll ping the tunnel. 10.1. Show you in simulation mode here. All right. And just to show you. No, that's ARP. Let's wait a few minutes. Skip. Here should be it. So here it's going to say destination directly connected right here, and then the packet receives needs to be encapsulated in GRE, and it gets encapsulated, right? And it's going to be sent over there, right? So that's pretty much it for MPLS and tunnels. Let's go ahead and move on to ACLs, or access lists, right? So what are access lists? They are a set of rules in the network designed to control network traffic, whether that be ingress or egress, or just coming coming into the network or leaving out of the network by filtering packets. They restrict unauthorized access, define policies, and regulate bandwidth usage. They are essential in routers, firewalls, and switches as well. They're able to block specific IP addresses, limiting access to certain services, or enforcing security policies. So how ACLs work? So they work by traffic filtering. ACLs compare packet headers to predefined rules to decide whether to permit or deny traffic. Sequential processing. So ACLs, let me see if I'm able to. Here we go. ACLs, sequential processing, right? So this is the ACL, or show access list, output of it. So an ACL will have ACEs, or access list entries, and it's basically this rule right here, just 10, 20, right? And since they're sequential, meaning they'll start at the top and work their way down to the bottom. At the top, if it matches this entry right here, then it will be denied. It will no longer look at 20 through 80. If it doesn't match 10, then it'll go on to 20, 30, 40, so on and so forth, right? Until it reaches 80. If 80 doesn't match it, then there's an implicit deny, meaning if it doesn't match any of these entries, it will automatically be denied access to the network. I'll be right back, okay? Give me 1 second. All right, guys, I'm back. All right, so it starts from top to bottom, the implicit deny, and pretty much covers the sequential part that it mentioned. Nope, here. All right, there's two ways to actually apply an ACL to an interface, because just creating it itself doesn't really do anything. It has to be applied to an interface first for it to actually start filtering for specific kinds of traffic. And there's two ways. There's inbound and outbound. And let me show you how that works as well. So inbound, traffic coming in to the interface here will be inspected. If it matches an ACL that's there, then it will be denied, or it will be let in, right? Outbound, traffic exiting or going out of this interface right here will be inspected. Again, it will be denied or permitted based on the ACLs configured on this device here. Again, they're implicit denies if no rules match. Packets are automatically denied by default, right? There's different types of ACLs as well. There's a standard ACL, focuses on source IP filtering, providing basic control for traffic management. So only source IP addresses this will check, the standard ACL. While an extended ACL provides more granular control, allowing you to filter for not only source IP, but destination IP as well, ports, as well as protocols like TCP, UDP, ICMP, things like that, as well as port numbers like 443, 80, 25, SSH, things like that, right? And it's more granular control. Named ACLs use descriptive names for much easier management and organization compared to numbered ACLs. Dynamic enables temporary or scheduled-based access control for flexibility and automation. We just showed you that as well. The ACL syntax. So it uses commands like access list followed by the entry number, permit deny, the IP address, and then it uses wildcard masks like the routing protocols. This one, it should be access list followed by the entry, then it should be permit or deny followed by the protocol, the source IP followed by the destination IP, and then it could be EQ equal then LT less than range, which is a range of ports that you want to either allow or deny. And I think that's it. We'll actually do a lab on it as well at the end of this, so we'll explore those ranges as well, right? Again, you have to attach the ACL to an interface using the command like IP access group 101 to enforce the rule. So IP access group in interface configuration mode is how you apply the ACL. Modifications, update or remove entries dynamically to adapt to evolving security requirements. How to read access list. So you can do access list 10 permits traffic from 192.168.1.0/24 network to allow a specific subnet. Or access list 101 permits TCP traffic from anywhere going to anywhere if the port equals 80, right? Just the easy way to read it. And this is the example of the standard access list, right? You see it's only source IPs. And here you can actually see an extended access list where it's protocols right here, hosts. So that you can use this word instead of /32, makes it easier. So denying host to anywhere, TCP, here's the ports, www is 80, which is HTTP, this is HTTPS, SSH. So it gives you much more granular control on what you allow inside and outside the network, right? And let's see, filtering criteria. Again, only source, while extended allows you source destination IP, protocol, and port. Extended allows you more granular control about the traffic that you let into and come out of the network. The ACL number range standard is, for standard, it's 1299 and 1300 to 199. And then extended is from 100 to 199 and from 2000 to 2699, right? And the best practices, so place the most specific one at the top so it can filter through those first, right? Documentation, maintain a detailed record of each ACL, purpose and rule detailed for easier troubleshooting, and test them in a controlled environment before deploying in production. Avoid overly complex ACLs to reduce processing overhead and potential errors. Security or the real-world cases. Block internal IPs attempting unauthorized access to internal systems or services. Regulate bandwidth by prioritizing critical services like voice over IP over less important traffic. Segmentation isolates sensitive subnets from general access to enhance security in enterprise networks. And mistakes in troubleshooting, misconfigurations, incorrect rule placement, or syntax errors can lead to unexpected traffic blocks. Performance issues, large or poorly optimized ACLs can increase devices like CPU usage and latencies. Visibility, use show access list or logging features to monitor rule activity and packet matches. And then the conclusions on ACLs are critical for network infrastructure and security, and offers precise control over traffic placement and enforcement. All right, and that's pretty much it. Let's go ahead and dive into the lab itself. So here, this is the lab where we can have fun, basically. So it's already configured. Yeah, so let's actually dive in. Let's make up a rule saying first let's do extended. And the best standard. The best practice for standard is place it as close to the source, to the destination as possible. So right here, this interface right here, this G0/0/0 interface on router 1. So we're gonna block traffic from this network from reaching this server right here, which is, let me make sure it's 2. Yeah, let me put 11. Let me fix that. Better. Let me put 2 here. So let me just show you that it's able to actually ping there. Make it like this. Way better. Now we can show you everything on the screen. So let's do ping 11.11.11.2, and then it should ping. Let's fast forward just a little, just to show you. See, perfect. First one fails because of ARP. Let me show you one more time. So we're gonna block this, right? So let's go into here and conf. Actually, we'll go into the other one because remember, it's as close to the destination as possible for standard ACL. So we'll do n conf t. We'll do that its access list followed by the entry, or the number, followed by permit or deny. So we're going to deny traffic from the 192.168.10.0 network 0.0.0.255, and that should be it, right? And remember, the ACL that alone will not do enough, right? You actually just creating it, you have to apply it to the interface for it to actually start working. So we'll do interface G00, and then it's IP access group followed by the number or word, and then in or out, right? We'll do outbound, right? So let's attempt to ping it again. I think this is the one. Nope, this one? Yeah, we'll try to ping it again, and it's already working. Destination host unreachable. And just to show you, we'll actually do this simulation and show you it being denied by the ACL. Whoops, fast forward too much. Let's do here. And this is it right here. Boom, boom. The device TTL on the packet, the outgoing has an outbound traffic access list with an ID of 1. The device checks the packet against the access list. The packet matches the criteria of the following statement: deny 192.168.10.0, 0.0.0.255. The packet is denied and dropped. Right? Now, will these be able to ping this server here? I'm gonna give you a second to lock in your answer. and we will show you. Let me copy this. And the answer is no. Remember, ACLs have an implicit deny rule. So even though we didn't explicitly deny this, there's an implicit deny that's there by default. So let's go ahead and do access list 1, permit IP any. Excuse me, permit any. I was thinking of extended. So let's do show access list and see it added that entry there as 20. Now let's try to ping it again and it should go through now this time without an issue. Perfect. So we've successfully blocked this traffic or blocked this network right here from communicating with the server while allowing this network here to communicate with the server without an issue. Now let's do extended. So extended, the best practice for extended is actually configuring it with to the close, excuse me, as close to the source as possible. So we'll deny, so we'll do access list, and then remember it has to be extended. So it has to be from this range right here. So we'll do 100. We'll do deny, and then we'll do SSH traffic. Now TCP traffic from 192.168.10.0 0.0.0 255, and then we'll do this interface right here to host, because it's a host a /32. It's just the easier way of doing a /32 subnet. So host 12, excuse me, 12.12.2. If the port, and these are the things you could do for the port, right? DSCP, that's for quality of service. EQ matches packets only for that explicitly defined range. So we use 22 for SSH. Greater than 22 if you want to deny telnet and anything above there, right? Less than, anything less than the specified range, 22. Match only packets not on a given port number. So everything besides 22 SSH, as well as the range command here. But for now, we'll do EQ. /22, and then do show access list. Do show access list. We'll remove the first one. It's gonna remove everything though, so let's do no access lists 100. Do show tag. All right, and then we'll do here, and then we'll apply it. Remember, extended is as close to the source as possible. So we're gonna apply it to this G000 interface, right? Interface G00 IP access group 100 and inbound. Right, because here we used outbound, here we used inbound. Right? Probably should have shown you it before. So we'll do, now we're able to telnet. So we'll do this SSH -L, and we'll actually configure some things here first. Host name first. Remember we did this earlier in a SSH explanation. It's up on the YouTube channel as well if you want to go and check that out. IP domain name example.com. Username, I'm gonna put myself. Secret for MD5 encryption, we'll just put CCNA. Enable secret, we'll put Cisco. And then crypto key generate RSA, and that should be enough. The key size will do 1024. Generated them, then we'll do line BTY 0 through 15, transport input SSH only. To allow only SSH, we'll do exit, and that is enough. Let's go here, SSH. We'll do the username followed by the IP address. 2. It's going to ask for CCNA. CCNA. Did I already forget it? No, it's secret. CCNA. Hold on. CCNA. Oh wow. Cisco. Give me 1 second. I figured out the issue. So we had to do login local for it to actually use the local database. So let's do line console, no, line VTY 0 through 15, login, local, for it to use the local user database here. So let's go ahead and try that again. CCNA, enable, and then this is Cisco, and then conf team, right? We're in the router now, right? So we'll do end, and again, and then we'll apply it to the interface and show you that you can't telnet anymore. So excuse me, SSH into that interface anymore. So we'll do IP access group in, try it again, and then fast forward. Connection was timed out, right? Let me show you it in simulation mode. This. Here it is. The receiving port has an inbound traffic class access class with a list. Jesus, I can't read it. The receiving port has an inbound traffic access list with an ID of 100. The device checks the packet against the access list. The packet matches the criteria of the following statement: deny TCP traffic from 192.168.10.0 0.0.0.0.255 to host 12.12.12.2 if the port equals 22. The packet was denied and dropped. Now, will we be able to actually ping this? Let's actually see. Lock in your answer. We'll just fast forward this a little. And ping 12.12.12.2. The answer is no. Why? The implicit deny that access list have. So we'll exit out of this. We'll scroll up to this, and then we will do IP any. So this is access list 100. Let me fix that to deny, to permit, permit IP traffic from anywhere going to anywhere, right? So now do show access list, IP any. Let's try to ping it now, and it should work. See? That implicit deny is very important to remember. I don't know why only 2 went. We'll do it again. There we go, right? Remember, implicit deny is going to be like important to remember when configuring access lists, because you may have just forgotten, and that may be the reason why your traffic cannot actually traverse the network how it's supposed to, all right? And that's pretty much all for today, guys. Thank you for tuning in, and see you in the next one. Bye.